This is a practice exercise from page 96 of the textbook. We're looking at determining an empirical and molecular formula through combustion analysis. So I can tell that this is combustion analysis because it says that combusting the substance produces carbon dioxide and water. So we should remember from the beginning of the chapter that a combustion reaction takes a hydrocarbon, and in this case our hydrocarbon is composed of carbon, hydrogen, and oxygen. So it's got carbon something, hydrogen something, oxygen something. It always reacts with oxygen, and in our case combustion is always going to produce carbon dioxide and water. So what we're trying to do in this combustion analysis is work backwards from the products of combustion to try to figure out the formula of the starting compound. So again, the products of the combustion analysis are carbon dioxide and water, and we're going to use that information to try to determine the missing information here. How many carbon atoms, how many hydrogen atoms, how many oxygen atoms. So looking at the information they give us, we know grams of carbon dioxide and grams of hydrogen. Considering these problems, think about how we balance combustion reactions. We typically balance the carbon and the hydrogen first because we know that all of the carbon in the carbon dioxide must have come from the original compound, and all of the hydrogen in the water must have come from the original compound. We don't try to balance the oxygen until the end because the oxygen shows up in every compound, making it very difficult to isolate. So typically when we try to determine empirical formulas, we try to figure out how many moles of each substance we have. So we need to know how many moles of carbon, moles of hydrogen, and moles of oxygen. Now the moles of carbon are going to be pretty straightforward. We can get the moles of carbon working from the grams of carbon dioxide. We can get the moles of hydrogen working from the grams of water. It's going to be harder to get the moles of oxygen because we don't have oxygen isolated in a compound. So what we're going to have to do is we're going to have to figure out how many grams of carbon and grams of hydrogen are in the original sample, and we will subtract that from the mass of the original sample to figure out how many grams of oxygen must have been present. So the first thing we're going to do is we're going to use the carbon dioxide to figure out how much carbon was in the original sample. Because again, looking at that reaction, all the carbon in the carbon dioxide must have come from the original sample. So I'm going to start with my 0.512 grams of carbon dioxide. I want to change grams of CO2 into moles of carbon dioxide. And again, using the periodic table to calculate molar mass, you should get 44.0. But I just care about carbon. So I'm going to cancel out the moles of carbon dioxide so that I can talk about moles of just carbon. And this is pretty straightforward. There's 1 mole of carbon in every mole of carbon dioxide. Again, this calculation may look pointless because it's not changing the numerical value, but we do need it to change our units because we want to be talking about just carbon, not carbon dioxide. Last thing we're going to do is change the moles of carbon into grams so that we can figure out how many grams of carbon were in my original sample. And again, using the periodic table, there are 12 grams in every mole. So if you do this math, you should find out that there are 0.140 grams of carbon in the carbon dioxide, and it means that that 0.140 grams of carbon must have come from my original compound. Now I can do the same thing with the water, and again, with the water we're doing this to figure out how many grams of hydrogen, since all the hydrogen in the water must have come from hydrogen in the original compound. So again, starting with 0.209 grams of water. We're going to do something very similar. Change grams of water into moles of water. Again, using the periodic table to get the molar mass there. Since we don't want moles of water, we just care about the hydrogen, I need to figure out how many moles of hydrogen are in every mole of water. This time, it's a 2-to-1 ratio, so we need to make sure that we've got the 2 in there. Last thing we do is we're going to change this to grams, so we know that a mole of hydrogen is 1 gram. And doing this math, we're going to get 0.0232 grams of hydrogen. From here, we can determine the mass of oxygen in the original compound. So we know that the original compound had a mass of 0.225 grams. We now know that 0.140 grams of that was carbon, and 0.0232 grams of that was hydrogen. So the leftover mass, which is going to be 0.0618 grams, must be oxygen. So now we're back in a familiar situation. We have grams of the three substances. We can change grams to moles because we know that chemical formulas are just mole ratios. So once we know the moles of the carbon, the hydrogen, and oxygen, we can find the mole ratios and use that to make our empirical formula. So this first portion is the only part of combustion analysis that is different from otherwise determining an empirical formula. Just use the information from the combustion analysis to work backwards and determine the grams of carbon, hydrogen, and oxygen. So let's go ahead and finish the rest of the problem. So if we know that we've got 0.140 grams of carbon, we know we need to change grams of carbon into moles of carbon. And that's going to give us 0.0117 moles of carbon. We're going to do the same thing for hydrogen. Converting grams of hydrogen into moles of hydrogen. Again, the reason we do this is not because the numerical value changes, but because it changes our unit. So now we are in moles of hydrogen, so you do need to show these steps so that I can see your complete work, even though it only changes the unit, not the numerical value. And lastly, we'll do this for the oxygen. So if we look, our oxygen is our smallest value here, so that's what we're going to divide everything by. So for carbon, we're going to get 3.03, and with rounding, that's about 3. For hydrogen, we're going to get 6.01, which is about 6. And obviously when we divide this by itself, we're going to get 1. So when I write the empirical formula, my ratio of carbon to hydrogen to oxygen is 3 to 6 to 1. So written as a formula, that's going to be C3H6O, since we don't write the number 1 in chemical formulas. So this here, this is our empirical formula. So if we look at the rest of this problem, now they're giving us a molar mass and they want the molecular formula. The only way we can do a molecular formula is when we have a molar mass. So what we're going to do is we're going to compare the molar mass of the empirical formula to the molar mass of the molecular formula to see what factor they're different by. So the molecular weight, or molecular mass of the empirical formula is equal to the mass of 3 carbons, 6 hydrogens, and the 1 oxygen. And again, remember, we are rounding the masses in the periodic table to 1 decimal place, and that'll give us an answer of 58 grams per mole. So we know that the empirical formula has a molar mass of 58 grams per mole, but the molecular formula has a molar mass of 116. Again, we want to figure out what the ratio of these are, so we put the larger number on top, so 116 grams per mole divided by 58 grams per mole. And we can see that these are different by a factor of 2, which means we need to multiply the empirical formula by 2 to make it a molecular formula. So C6H12O2 will be our molecular. So as you can see, this combustion analysis is extremely similar to what we do with the empirical molecular formulas normally. The only difference was the portion at the beginning where we had to figure out the grams of carbon, hydrogen, and oxygen. So when you're doing combustion analysis, the beginning's a little bit different, but the ends of the problems, finding the empirical and molecular formulas, exactly follow the patterns we've been using before.